Without further ado, let me introduce our first speaker, Robert Brandenberger, who's joining us from McGill, who has worked in a variety of topics in physics, and he's going to tell us today about emergent space and its observational signatures. So take it away.
Okay, so the main message of my talk is going to be that it will be possible to probe fundamental natures about space and time with cosmological observations. So that's going to be the main message. Now, I will have some provocative parts in my talk, which could lead to topics for discussion. I will also have parts in the talk where I speak from a completely naive point of view, from the point of view of philosophy, and maybe you can help me, but I will proceed in the naive physicist approach. So since this is a first talk, and a lot of the talks about cosmology, I also want to give a little bit of framework, and I want to talk a little bit about the data that we have, and we will get more data. So anyway, this is the rough outline. Observations, paradigms of early universe cosmology, and I want you to focus on the S in paradigms. There is not just one paradigm of early universe cosmology, as those of you based in the United States might have been led to believe. Okay? I'm not in the United States, I'm in Canada. There are several paradigms, and I'll try to show you how and why. But I'll spend some time on the standard paradigm, which is inflation. And in particular, there's an issue there, debate on inflation. And there's been a debate in Scientific American on whether inflation is good or bad. And I'll try to explain a little bit what this debate is about, and this is a point where probably philosophers can help. So then I will turn to one of the alternatives to the standard cosmological paradigm, which I will call emergent cosmology. And by that I mean that there's an early phase of the universe in which there is no space and time as described by your usual theories, and suddenly there's a transition to something which is standard Big Bang cosmology, and then we have observations. So this is what I mean by emergent cosmology. This is not Padmanabhan's approach to emergent cosmology. It is not Verlinder's approach to emergent cosmology. So then I will show you how you can take a model of emergent cosmology and derive observational predictions from it. Then I'll conclude. So, observations. So we have instruments, telescopes at beautiful points on the surface of the Earth, optical telescopes, with which we see galaxies. We look further than galaxies. If we take a full sky projection onto a plane, each of these dots is a galaxy. The main point is that galaxies are not uniformly distributed. There's structure in the distribution of galaxies, and this is the data which we want to explain. There are microwave telescopes, again, high on the Andes, on the South Pole. McGill is involved in this telescope. There are even some telescopes in outer space. And with these telescopes, you look at the microwave radiation, which is coming to us from different directions in the sky. And so with these fairly expensive instruments, you get this beautiful all-sky map of the temperature distribution of the microwave background. So different colors mean different temperatures. Different colors mean different temperatures. So uniform to a very high level, the microwave is isotropic, and that's a data point. Now, if you look at temperature differences 1 part in 10 to the 5, then you start seeing the differences in temperatures. So hot spots, cold spots, different colors mean different temperatures. With such a beautiful map, you stick it into a black box called statistic, and out you get a boring plot. So you get amplitude as a function of angle in the sky, large angle, small angle. And if there was no structure in the sky, the data would be 0. The data is not 0, so there's lots of interesting structure in the sky. There's this flat region, large angular scales. There's this peaky structure on scales of about 1 degree. This is data. And you see the black dots are the data points with some statistical errors, small angular scales, systematic uncertainties, large angular scales, and an artist painted a red curve which fits the data fairly well. And I'm going to tell you a little bit about who the artist was. Okay, so I'm a cosmologist, and I'm really excited about the field of cosmology because it combines basic questions of philosophical nature, origin and early evolution of the universe. What is a Big Bang? Was there a Big Bang? What was before the Big Bang? Nature of space and time. But there's hard data that we want to explain. We want to explain the observed large-scale structure, so the distribution of galaxies, microwave anisotropies. And then a good theory, a good model, ought to make predictions for future observations. So we want to go out on the limb and take a model of emergent space-time and make predictions for future observations. And I'm going to make this link in the talk. Okay, so the point for philosophers is that I strongly believe that the fundamental nature of space and time on the smaller scales can be observationally probed. So what is the framework of cosmology? So the universe is space and time and matter, which lives in space and time. You cannot neglect the matter. So now in terms of late-time cosmology, we describe space and time using Einstein's theory of general relativity. And we can use a classical physics description of matter, hydrodynamics. And if we add the assumption that the universe is homogeneous and isotropic, which is now well proven by the isotropy of the microwave background, then we find that the universe cannot be static, but it is expanding, and it was expanding even faster in the past. So, and this is the image which I want you to keep in mind for the expanding universe. Space is a dough, galaxies are raisins. You stick the dough in the bread, space expands, each galaxy is at rest in the dough, but the separation of galaxies is increasing. The further away a galaxy is from us, the larger the apparent velocity. So if we run the clock backwards, we find that in the past, the temperature was very large. It was so large that you have to take particle physics and quantum effects into account. And if you take particle physics, atomic physics into account, then you find that according to this standard Big Bang cosmology, there is a black body microwave background. So this is a prediction that came out of standard Big Bang cosmology. And I want to emphasize prediction because when standard Big Bang cosmology was developed, we hadn't measured the microwave background. And the famous Russian physicist Zeldovich is supposed to have said, when he heard about standard Big Bang cosmology, he was supposed to have said, this cannot possibly be right, because if standard Big Bang cosmology is right, there would be a cosmic microwave background, and there is no cosmic microwave background. So you see, standard Big Bang cosmology was predictive in an incredible way. So if you look at one point in the sky, and you take the microwave background, you run it through a spectrometer, and you look at the intensity distribution, different wavelengths, different intensities, then you get this curve, this intensity curve. And you see, those of you who've studied thermodynamics will recognize that this is a black body. But this is actually the microwave background spectrum, including errors. The error bars are smaller than the thickness of the line. So cosmology has become precision science now. And so this is the picture of standard Big Bang cosmology. We are observing the universe here at late times. Time goes back. This is the period where the microwave background was released. And then if standard Big Bang cosmology is applicable further in the past, then we get this strange singularity called the Big Bang singularity. Okay, standard Big Bang cosmology had an incredible success, namely the isotropy of the microwave background. So, the black body nature of the microwave background. So the prediction of the existence and black body nature of the microwave background. But standard Big Bang cosmology exactly cannot explain the isotropy. And this problem I sketch in this space-time plot. So this is space. Vertical axis is time. This is the time when the microwave background was released. And the lines at 45 degrees, those are lines that light travels on in space and time. So stuff that travels at the speed of light travels in these 45-degree lines. So we observe the microwave background coming from these scales. But in standard Big Bang cosmology, you can causally only explain isotropy on a much smaller scale. So therefore, in standard Big Bang cosmology, you cannot explain the isotropy of the microwave background. Neither can you explain the existence of anisotropies in the microwave background on large scales. And this problem I sketch here in another space-time sketch. This is space, and I'm using coordinates which are fixed in the expanding dough, so-called co-moving coordinates. So if you visualize a fluctuation as a standing wave with a particular wavelength, that wavelength, the physical wavelength, is increasing, but measured in terms of measuring rods which expand as space expands, the wavelength is fixed. So this is a wavelength on which we observe structure. Structure had to be created in the early universe. The problem is that the wavelength on which we want to explain the existence of interesting non-random structure is much larger than the causal length, the horizon, at early times. So in standard Big Bang cosmology, there is no causal mechanism for the origin of structure. So now all physicists will obviously be bored by this statement. They will have heard this statement many times. But philosophers should be a little bit skeptical about this statement because I'm actually sticking in two lies in this statement. So what I said is exactly what is written in all cosmology textbooks, but there are loopholes. There are two loopholes, in fact. So for the graduate students here, find the loopholes. Okay, but anyway, if we want to explain the data of the large-scale structure in the universe, we need new fundamental physics. And in turn, the new fundamental physics can be probed by the data. So this is a relation between fundamental physics and data. So this was an introduction to the data that we have. And now I want to turn to the paradigms. How do we think now that we can explain the origin of this interesting structure in the universe? And I want to emphasize the S in paradigms. So I first want to give a little bit of history. I want to show a plot from a paper 10 years before inflation. This comes from a paper of Zeldovich and Zuniaev in 1969, 1970. This is 10 years before inflation was discovered. So this is a sketch of space and time. And this 45-degree line is the horizon. And where this 45-degree line turns over, that's the time when the microwave background was released. Now, what Zeldovich and Zuniaev postulated is they said, let's assume that there was some unknown mechanism in the early universe which creates standing wave fluctuations, inhomogeneities, indicated by these structures. Now, as I will show later on, if you have fluctuations on scales larger than the horizon, these fluctuations just sit there as standing waves. They don't oscillate. Whereas on scales smaller than the horizon, they oscillate. So that's the role of horizon, but I have to correct myself. It is Hubble Radius, which is the inverse expansion rate. Okay, so this is what Zeldovich and Zuniaev postulated, some mechanism producing standing wave fluctuations. These standing waves start to oscillate when they enter the horizon. And this predicts these oscillatory features in the angular power spectrum of the microwave background. So, anyway, So these oscillations in the angular power spectrum of the microwave background, these ones, were predicted back in 1970, 1969 by Zunaev and Zeldovich, and in a parallel paper by Peebles and Yu. And this is what you need. So any model of the early universe that produces scale invariant, and I'll explain what scale invariant means, fluctuations on large scales, that will produce these acoustic oscillations in the CMB angular power spectrum. So the artist who drew this red curve these two artists were Zunaev and Zeldovich. Okay. So now, why do fluctuations, density fluctuations, produce microwave anisotropies? This I try to explain in this space-time sketch. Space and time. We are at T0 looking at the microwave background coming to us from different directions in the sky. And if there are inhomogeneities in the universe, then the surface of constant temperature is not going to be at the same time everywhere. It's going to fluctuate. Photons are emitted at the same with the same frequency on this surface. But this photon travels less far to us than this one. So the light will have been redshifted less for this photon than this photon. So density fluctuations produce microwave anisotropies. So the density fluctuations which Zeldovich and Zunaev postulated, they give rise to these microwave anisotropies. Okay. Now, you also predict, so this is the second part of the same plot out of the 1970 paper. You predict oscillations in the spectrum of the distribution of galaxies, the so-called baryon acoustic oscillations for experts. It's all predicted in 1970. Okay, so now, where does that leave inflation? So the question which Peebles and Yu and Zeldovich and Zunaev did not address is, where do these fluctuations come from? They were just postulated. And in fact, inflation is the first scenario based on fundamental physics, which explains the origin of these fluctuations, but it is not the only one. Okay. So now a technical point. In early universe cosmology, you have to differentiate between two length scales. One length scale is the horizon, and the horizon that tells you how far information can travel from the Big Bang. So the horizon is the region of causal contact. But then there's another length scale, which is the inverse expansion rate of the universe, which is called the Hubble Radius. And the Hubble Radius plays a role in terms of how inhomogeneities evolve. So if you have inhomogeneities with a wavelength greater than the Hubble Radius, they just sit there. They don't oscillate. Fluctuations with a wavelength smaller than the Hubble Radius, they oscillate. So if you are interested in structure formation in the universe, it's the Hubble Radius which plays a very important role. And in standard Big Bang cosmology, the Hubble Radius is the same as the horizon. But that's why standard Big Bang cosmology cannot explain the data. So any scenario of the early universe which can explain the data has to have the horizon being different than the Hubble Radius. So now I'm going to list a set of criteria which a successful early universe scenario has to satisfy. So the first one is exactly the Hubble Radius. The horizon has to be much, much bigger than the Hubble Radius. Otherwise, you can't explain the isotropy of the microwave background. Then, second condition is that if you want to create fluctuations using physics, then the scales, the length scales that we observe today have to start out smaller than the Hubble Radius, because you can't create fluctuations on scales larger than the Hubble Radius, because nothing oscillates on scales larger than the Hubble Radius. Again, I'm sneaking in a lie in that last statement. So then fluctuations need to evolve for a long time on super Hubble scales in order that fluctuations, if they are of quantum origin, become classical. So if you just want to create fluctuations classically, then you don't need this third point. And finally, the mechanism that satisfies the three first criteria has to create a spectrum of fluctuations which is scale invariant. And scale invariant means that if you take a sphere of radius r, then the root mean square density fluctuations in this sphere is independent of the radius of the sphere. That's what scale invariant means. So these are the criteria for successful early universe cosmology. So now I'll run through a couple of examples of models of the early universe which satisfies these criteria. The first one is inflation. And inflation is the idea that in the early universe, there was a period of finite duration between t sub I and t sub r when space expanded exponentially. That's the idea of inflation. So there's a big bang in inflation, so a singularity. Then there's this period between ti and t sub r when space expands exponentially. So let's first look at the horizon, the distance that light can travel. Between the Big Bang and the beginning of inflation, the horizon might increase linearly. But once space starts to expand exponentially, the horizon expands exponentially as well. However, the Hubble radius, the expansion rate, is constant during inflation. Exponential expansion of space means constant expansion rate. So Hubble radius is constant. So inflation provides a mechanism that makes the horizon exponentially larger than the Hubble radius. So the first criterion is satisfied. Length scales, the physical wavelength of length scales increases exponentially during inflation. So follow the red curve. You see that if inflation lasts sufficiently long, then the red scale starts out smaller than the Hubble radius. So it is possible to create fluctuations causally. Criterion 2 satisfied. Fluctuations evolve for a long time on super Hubble scales, so they can become classical. Criterion 3 satisfied. And the scale invariance of the spectrum, which I'm not going to emphasize here, that follows from the time translation invariance of this picture. Okay. Second paradigm that can explain the data is a bounce in cosmology. And here I'm giving you the most simple bounce in cosmology, where you assume that there was a contracting phase, which is the mirror inverse of the observed standard Big Bang expanding phase. Mirror inverse. And there's some new physics that creates a transition between contraction and expansion. So this is the size of the universe as a function of time. Bounce point, standard Big Bang expansion, contraction. So in the top part of this graph, I have a space-time diagram. Horizontal axis space, vertical axis time. And the Hubble radius is coming in. It's decreasing in the contracting phase, increasing in the expanding phase. I'm using co-moving scales. The physical wavelength is constant. So first of all, time runs from minus infinity to plus infinity. The horizon is infinite. Fluctuations start out smaller than the Hubble length, so causal structure formation possible. They propagate for a long time on super Hubble scales, classicalization possible. And if the contracting phase is matter-dominated, then vacuum perturbations become scale invariant. That last point I did not explain, and I'm not going to explain it. I can explain it to you afterwards. So this is an alternative to inflation. The one that I'm going to focus on is the emergent universe, where I'm going to assume that there's a new phase, maybe not even described by space and time, and then there's a transition to the usual standard Big Bang expanding phase. So time, and the vertical axis is size of space. So this is a corresponding space-time diagram. Space, time, the emergent phase, static, or maybe usual space-time interpretation doesn't even exist. Hubble radius is infinite. Once standard Big Bang takes over, the Hubble radius starts very small and starts to increase. So the blue line is the Hubble radius. The red line, that's the physical wavelength of fluctuations, which we observe today. Okay, the horizon problem. If the emergent phase is long, the horizon is huge compared to the Hubble radius. First criterion satisfied. Fluctuations start out sub-Hubble. It's possible to create them causally. They propagate super-Hubble. Scale invariance will come. Okay, so there's not just one paradigm of early universe cosmology which can explain the data. There are several. And this was not an exclusive list, because all I want to emphasize is that there's more than one. And I want to mention the emergent one because I'll come back to it. However, inflation is the standard paradigm because it was the first. So I'm going to give a brief review of inflation. I'll address the recent debate on inflation, and I'll talk about conceptual problems of inflation. So, this is why inflation attracted so much attention, because it is the first scenario based on physics which explained the problems of standard Big Bang cosmology, and it provided a causal mechanism for the generation of fluctuations. Chibisov and Mukhanov, 1981. So, this inflationary paradigm is based on general relativity to describe space and time, and matter, which is a scalar field. And inflation is a phase in which space expands exponentially. And if you work in the context of general relativity, you need matter with pressure almost equal to minus energy density, which is not the usual matter you know of. And this is why physicists introduced a scalar field in order to give this kind of matter, and a slowly rolling scalar field. And the reason they introduced a slowly rolling scalar field, because with scalar fields you can do anything. You can do anything. In particular, you can generate exponential expansion of space, provided that this scalar field is slowly rolling. Because scalar fields have potential energy. Fermionic fields, regular fields, don't have potential energy. And potential energy has negative pressure. So therefore, if potential energy dominates, you have a chance of getting pressure equals minus energy density. If for potential energy to dominate, the scalar field has to roll slowly, because otherwise the kinetic energy dominates. Okay. So inflation is a period in the early universe of finite duration where space expands exponentially. So if this is the value of this scalar field, you postulate some potential, the simple potential, then the idea is that inflation starts when the scalar field is here. The scalar field slowly rolls down the potential, and eventually it will oscillate around its minimum and disappear. I will talk about what disappear means. It doesn't really disappear, but it does interesting things. And this gives rise to this space-time diagram. So this is what inflation does. Okay, so inflation is the first theory based on physics that gave cosmological perturbations. But opinions of the people who are responsible for developing inflation now disagree vehemently. And I'll give you these quotes. There's Andre Linde from Stanford University, who basically says inflation is great. It made predictions which have been confirmed with observational data. Then on the other hand, you have Paul Steinhardt. Paul Steinhardt worked on inflation at the same time as Andre Linde. And they basically say that experimental data disfavor the best motivated inflationary scenarios and introduce serious conceptual difficulties. Initial condition problem, multiverse problems, and inflationary unlikeliness problems. See, these are people who in 1982 worked on exactly the same thing. They proposed the second inflationary scenario, and this is how their views on inflation now disagree. In fact, Anna will be here.
Unfortunately, she had to cancel for personal reasons.
Okay, so in that case, someone else has to defend her point of view. So let's go on and see what Alan Guth thinks. He comes along, he says the same things as Andre Linde. Specific quantitative predictions. Now, the person who did the first calculations of cosmological fluctuations, Slavoj Mukhanov, what does he say? He says the multiverse and eternal inflation damages the predictability, the predictive power of the theory. So he comes down on the side of Paul Steinhardt. Okay, so diverging views on inflation. So now, what is my view? So now my view is a very naive view. Unfortunately, I'm not at all a philosopher, so I need help. So for me, history is important and making predictions is important. So for me, I would say that inflation was successfully predictive, and it continues to be so. And this is exactly what Slavoj Mukhanov would say. So inflation predicted before the data this red curve. Because when inflation was developed, we didn't have the data of cosmic microwave background anisotropies. It predicted that the universe was approximately spatially flat. And it continues to make predictions. For example, it predicts that gravitational waves will be found on large scales with a small amplitude and with a slope which is red. Means less power on small wavelengths than large wavelengths. So inflation. So if any of these data would have not been correct, then the simplest inflationary model would have been ruled out. And you see, if the simplest realization of inflation doesn't work, then my opinion would be, why should you continue? Why should you fine-tune a scalar field model just to fit data? Because then all you're doing is you're replacing one problem by another. So I think both Slavoj Mukhanov and I would give up on inflation if the simplest models don't work. But we would say that inflation definitely is predictive. It has been successfully predictive, but it is not unique. You can't show that the data proves inflation. Now, in terms of initial conditions, you can also show that in the context of simple models of inflation, inflation is an attractor in initial condition space, except for spatial curvature, which you have to tune. So in terms of initial conditions, fairly generic initial conditions will give inflation. So in my view, inflation does fairly well in terms of initial conditions. Now comes the most controversial comment, which both Slavoj Mukhanov and I would say. So we would say that the multiverse, which you hear a lot about, especially in the United States, the string inflationary multiverse is neither a prediction of inflation nor a prediction of string theory. So the multiverse is based on stochastic eternal inflation, stochastic effects, driving the scalar field up a potential. These effects only are important for field values where we have absolutely no control of the physics. And while string theory, we don't understand non-perturbative string theory. So when people talk about vacua of string theory, there's no basis to talk about that. So neither string theory nor inflation give rise to a multiverse. So this is obviously a provocative comment that I'm making. But from my point of view, the problem is, for inflation, is that there are conceptual problems with the scenario. And this is a list of problems. We would like to know what is the matter field that gives rise to inflation. We don't yet know it, even after 30 years of work. The physics that is used to get inflation is probably not applicable at the scales where inflation works. And the idea of having potential energy give you exponential expansion of space is subject to the cosmological constant problem. So I think I don't have too much time now, so maybe I'll run through. So here's a space-time diagram of inflation, which you saw several times before, and I added one length scale, this length scale in purple, which is the string length or the Planck length. We know that standard physics breaks down for wavelengths, for lengths smaller than that purple line. Nevertheless, the fluctuations emerge from that zone of ignorance. So even if inflation is right, we need Planck scale physics. We need to know the nature of space and time in order to make reliable predictions from inflation. So this is a trans-Planckian problem. Inflation has a period before inflation. It is incomplete. It does not solve any of the philosophical problems associated with its singularity. And finally, this is the problem I want to emphasize. There's a major problem in fundamental physics, which is the cosmological constant problem. Vacuum energy predicts a very large cosmological constant, which we don't observe. Potential energy is equivalent to vacuum energy. So how can we use potential energy to drive exponential expansion of space when vacuum energy doesn't gravitate? To me, this is the Achilles heel of scalar field-driven inflation. Then inflation happens at very high energy scales, and we don't understand physics at very high energy scales. So I think based on these conceptual problems of inflation, we should look at alternatives. So and I want to explore the emergent paradigm, the emergent cosmology paradigm, and I want to show you how we can make predictions from that paradigm. And I will use a toy model of the emergent universe paradigm, which is called string gas cosmology. So emergent cosmology. I have 10 minutes?
Yes.
Okay, good. Okay, so the emergent cosmology is the idea that there's a phase which doesn't have the usual description based on Einstein's theory of general relativity. It's some new phase, which we don't know much about. Maybe some of you know more about than I. So it's very dangerous for me to talk about this, and so I need a toy model. So I'm going to tell you about a toy model of emergent cosmology. And this toy model is based on superstring theory. And this is not less dangerous for me because I'm not a superstring theorist either. So if I want to talk about string theory, superstring theory, I need a helper. And this is the helper that I pull out of my pocket. This is my fundamental superstring. So according to superstring theory, the fundamental objects are not point particles, but string-like objects. And string-like objects can do things to space which point particles can never do. This is space. I'll assume that space is finite, toroidal in all dimensions. And you see, a string can wind space and prevent it from expanding. Point particles cannot do that. So the toy model of emergent cosmology, which I'll explore, is based on taking the fundamental new degrees of freedom of string theory, which are the oscillatory modes of strings, which point particles do not have, and the winding modes, and see what effect these could have on the early universe. So the oscillatory modes, they give rise to the fact that a gas of strings has a maximal temperature. A gas of point particles does not have a maximal temperature. You take a gas of point particles, you compress it, temperature goes to infinity. You take a gas of fundamental strings, you compress it, temperature initially rises, it levels off, it decreases again. Fundamentally different. You get a fundamentally different picture of the early universe. The fact that you have winding modes and center of mass motion of a string leads to a new symmetry, which says that physics at large geometrical scales is equivalent to physics at small geometrical scales. A very different picture of the early universe that follows from this. This is called T-duality, the symmetry. So this is the way that the temperature of a gas of strings behaves if you take a box with radius r and you decrease the radius of this box. It's a bell-shaped curve. So there's going to be a region of radii where the temperature is almost the same. This is the model of the emergent phase, and the word that string theorists give to this phase is Hagedorn phase. Okay, so now we are going to assume that space is static in the Hagedorn phase, in this emergent phase. And then there's a transition where the windings disappear, and then that allows the universe to expand. And the way that windings disappear, if this is one dimension of space, you can have two strings intersecting, forming two loops. Windings have disappeared, space can expand. This allows exactly 3 out of the 9 spatial dimensions of string theory to expand. The other ones remain compact. So we've also explained the reason why we have 3 spatial dimensions which are large. Okay? So now how do we get observational predictions from this paradigm? So we start with this early phase, and this early phase has fluctuations. It's a hot gas of strings. In a hot gas, there are thermal fluctuations, and if the fundamental degrees of freedom are strings, then there are thermal fluctuations of strings. Okay, so the emergent phase has fluctuations. The fluctuations seed density perturbations and they seed gravitational waves. And we will use the usual theory to evolve the fluctuations. Okay, so you see I'm quite close to the end of the talk. And I think you'll all admit that I've been quite lenient on you, on the philosophers, in terms of having essentially no equations. So now, to show you that I'm actually a physicist and not just a philosopher, I'll have a short section with equations. And I just want you to take away the message how we do the calculations, not the details. So we are interested in fluctuations of matter and fluctuations of the metric. And these fluctuations are small in amplitude, and so we can calculate them in linear theory. So we take the metric, so space and time, which is the top line. We take matter, which is the second line. And we take homogeneous background, which is the blue. And we add small amplitude space-dependent fluctuations, which are the red. So there's a red metric fluctuation, the capital phi, matter fluctuations, delta phi. And they are not independent, because if you stick down matter here and not here, you'll produce a metric perturbation here and not here. So the two red variables are actually related. There's only one independent variable, and this independent variable is most easily written in this combination. This is the variable in terms of which the action has a form of the simplest form, the only form which physicists know how to quantize, which is that of a harmonic oscillator. Physicists reduce everything to harmonic oscillators. So we take general relativity and matter. We look at linear fluctuations about an expanding background. We reduce everything to a harmonic oscillator equation. And this is the harmonic oscillator equation. Each wavelength evolves independently according to that top equation. And this top equation shows you that fluctuations on large wavelengths are frozen in. On small wavelengths, smaller than the Hubble radius, they oscillate. If you start with vacuum fluctuations, and this is the initial condition, so initial condition equation, you can calculate predictions. So in inflation, you take vacuum initial conditions, you evolve the fluctuations, and you calculate them today, and you get this red curve, which I showed at the beginning. We want to do this calculation for emergent cosmology. So we have a thermal gas of strings, which creates density perturbations and gravitational waves. We compute them, and then we evolve them in the standard Big Bang phase. So what do we use? So we calculate the density perturbations, the metric perturbations, which give microwave anisotropies. They are given by the density perturbations. The gravitational waves are given by the pressure perturbations, off-diagonal pressure perturbations. So you see, these are complicated equations. So we have to compute very complicated objects here from string theory, and that gives us observables. Okay, so the density perturbations in a thermal gas are given by the specific heat capacity. Specific heat capacity in a volume of radius r has this holographic scaling, r squared, not r cubed. Put this together, and what you get is the perturbations that give microwave anisotropies, which have this form. So it's an equation which tells you how this the spectrum of fluctuations on a particular wave for a particular wave number k, how this depends on k. Okay. So k is a wave number, and this side tells you how the amplitude depends on k. Okay. First side, k doesn't appear. Therefore, you predict the scale invariant spectrum of density perturbations like inflation. If you look a little bit more closely, this temperature T is actually the temperature when the scale crosses the Hubble radius. For each k, the T is a time when the red and the blue curves cross, and there's a slight k dependence, and that gives a slight red tilt, like for inflation. So this picture of emergent cosmology can reproduce the same successes of inflation, but it did it after the observations. After the observations. So you see, inflation, at this point, inflation and emergent cosmology, string gas cosmology, are not exactly at the same footing, because inflation was predictive, string gas cosmology was only post-predictive. So we have to make predictions. Predictions, gravitational waves. H stands for gravitational waves. We predict the k dependence of the amplitude of gravitational waves. We find k doesn't appear, scale invariant. We look a little bit more closely. We find that there is a blue tilt in the spectrum of gravitational waves, which is predicted from emergent cosmology, not a red tilt, like inflation predicts. So at this point, we are making a prediction from emergent cosmology with which emergent cosmology can be distinguished from the current paradigm. Okay, so now will come the second very provocative comment that I'm going to make. Okay, and this, I'm going to show you how close emergent cosmology is to being able to make predictions that can be measured. So this is data from the BICEP experiment. All of you in the United States will have heard about the BICEP experiment. The BICEP experiment showed this plot in March of 2014. So again, this is angular scales, large angles, small angles. This is the amplitude of microwave background polarization, which is interpreted as coming from gravitational waves. So black dots is data with the error bars. The solid red curve is a background. The dashed red curve is a prediction of an exactly scale invariant spectrum. Inflation predicts a red tilt, meaning more power on large wavelengths than small wavelengths. So inflation predicts a curve which is tilted down here, where string gas cosmology predicts a blue tilt, a spectrum tilted up. Okay, up. Now, when this data was put out, press conference said, inflation has been confirmed. Okay, see the data? Data obviously shows that the spectrum goes down. Okay. The PIs of the experiment knew about string gas cosmology at the time of the press conference, because I told them before the press conference. I emailed them. No response. No response. There's a famous video coming out of Stanford with official Stanford header and trailer involving Andre Linde. Okay, so now it turns out that this data is probably foreground. It is not cosmological background. But we will soon have data of this type from telescopes such as Atacama Cosmology Telescope and South Pole Telescope, which may see the actual primordial signal. And then we will see if the primordial signal actually has a red tilt, it will be yet another prediction of inflation which has been verified. If it's a blue tilt, then Slava Mukhanov would throw away inflation. And this scenario of emergent cosmology would have made a successful prediction. It wouldn't show that it's correct, but it would certainly show that you can make predictions from emergent cosmology. So the last thing I want to say is, in what sense do the predictions which I made from emergent cosmology from my toy model of strings, do they really depend on strings? So I used an emergent phase. I used the fact that the density perturbations had a holographic scaling, which means that the density perturbations depend in a fixed volume, dependent on the area, not on the volume, r squared, not r cubed. And this comes out of string theory. And then I also needed that at the onset of the standard Big Bang phase, I could use general relativity for the long wavelength fluctuations. So these are the inputs which I needed in order to connect the emergent universe with data. Okay, so space-time continuum picture will probably break down in the ultraviolet in the early universe. So probably the existence of something like an emergent phase is natural. There will be fluctuations in this phase. For example, if this phase is thermal, there will be thermal fluctuations. If this phase is described by some other principle, it might be holography a la Verlinde or Padmanabhan, you'd also get scale invariance. It might be a spectrum inherited from some contracting phase. Now, I think that if the spectrum that emerges is approximately scale invariant, it will have a slight red tilt because of the space-time diagram that I showed. And I think that the spectrum of gravitational waves will have a slight blue tilt. So I think these predictions which I made in the context of a simple model of an emergent cosmology will probably be more general than that, but they're not completely general. So I've exhausted my time, so let me leave you with the conclusions. So the most important conclusion is that cosmological data can only be explained using new fundamental physics, but therefore you can probe fundamental physics using the data. So we have the current paradigm of early universe cosmology, it's inflation, but inflation has conceptual problems. I showed you an alternative, which is based on emergent space-time. This makes predictions. I think something that's quite clear is that you have to go beyond general relativity, classical general relativity, beyond point-particle effective theory, and beyond inflationary theory to really understand the early universe. But whatever the early universe is, you can test it with cosmological observations. So thank you.
So we have a few minutes for questions, and I'll use my position as chair of the session actually to ask one that comes up immediately. So I was thinking about the Trans-Planckian problem compared to the string gas cosmology picture, and is it because of the Hagedorn temperature that you have a kind of cutoff at the energy scale, whereas in the case of inflation, there's a concern about the level of fluctuations that are the ones that are stretched to be important for structure formation, and that you don't have theoretical control over the Trans-Planckian fluctuations. But in the string gas case, because of the limiting temperature, you don't have something similar? Is that?
Okay, so the Trans-Planckian problem for inflation comes from the fact that the early universe was expanding exponentially. Mm-hmm. And this the end of inflation is at a very high energy scale. It's about the scale of ground unification. Now you see that this red curve, which is the physical wavelength of fluctuations, is much larger than the Planck length at the end of inflation.
Right.
It is about 1 millimeter. And in emergent cosmology, that is the wavelength that it has throughout.
Okay.
It never has a wavelength smaller than 1 millimeter.
Okay.
So it's for this reason that the Transplanetary problem for fluctuations doesn't arise.
Right.
It also doesn't arise in a bouncing cosmology,
Great.
in a non-singular bouncing cosmology for the same reason.
Great. Any other? Yes, Simon.
Is that to say that then you really do need the string, the string component to the? Could you
No.
say that just a bit? My question is, do you really need the string theory? From that exchange, it wasn't intended.
No, based on the answer that I gave, in order to just look at the fluctuations in emergent cosmology, you don't need the string theory for the evolution. Whereas in inflation, you do need new fundamental physics in the early phase. So where I use string theory for is the initial conditions for the fluctuations. And so you might, if you have a different view of the emergent phase, you will just need to replace my string initial conditions by your initial conditions. But then your use of the equations for cosmological perturbations is well justified.
Hi. So what I think cosmologists really learn from the whole bicep
Again, would it be possible to speak up a little bit?
So what I think cosmologists really learned from the whole bicep event was the unfortunately very large uncertainties associated with dust in our own galaxy. So you talked about measuring or testing this model with the Atacama Cosmology Telescope, for example. But that will really depend on how large this blue tilt is predicted is. So how large is that, and do you have a sense of how that measures up to the now revised dust uncertainties?
Okay, so I can answer only half of your question, namely the predictions. So now my answer is going to be specifically to string gas cosmology. In our toy model, we have two free parameters: the string length and the closeness to the initial temperature to the maximal temperature. Two free parameters. We compute 4 observables. We have 2 consistent simulations. One consistent simulation tells us that the blueness of the gravitational wave tilt is equal in magnitude to the redness of the tilt of cosmological perturbations.
So 0.04.
Yeah.
I'd be interested to know whether ACT is actually going to do well enough to test that. I think you might be waiting for a next generation survey 10 years down the line.
I think you might be correct.
Yeah. Okay.
Great. Well, I'd like us to thank Robert, and we'll hold questions.